we're going to prove a fundamental elementary fact in group theory that each element in a group has a unique inverse. And we're going to do this very carefully, step by step, highlighting how the group axioms come into play. So let's assume that there are two inverses x and y for A, and we will prove that x is equal to y. Since x and y are arbitrary, this will finish the proof. So let x and y be inverses for A. Okay, so that's what we're going to start off with, and we're going to prove that x is equal to y. Here I'm going to highlight something very fundamental, which is the group axiom for an inverse. What does it mean for something to be an inverse? So here's a group axiom. It's usually the fourth axiom in groups after closure with respect to the operation, associativity, and existence of an identity. Okay, so it says existence of inverses. In the case of x being an inverse of A, we know that AX is equal to E is equal to XA, where E is the identity in G. Okay, so where E in G is the identity. So that's the axiom for inverses, and we're going to basically observe that in this axiom, this says that X is a right inverse of A, this equality, and the second equality says X is a left inverse of A. Okay, and this is going to be very crucial. So in order to show that X and Y are equal, being both inverses of A, we're going to do the following. We're going to basically multiply A and X. Okay, so we need to use what we know. Okay, that's how math proofs always go. Think about what you know this for X, and you also know the same thing for Y. Okay, if you replace Y in that equation, because we're assuming Y is also an inverse of A. So you have to manipulate these somehow. That's how you come up with this. So basically we say X is equal to X times E. Okay, that's using the fact that E is identity. Okay, so X is equal to X times E. Now what I'm going to do is I'm going to write this as X times A times Y. So what have I done here? Well, basically I'm trying to bring Y into the picture. Okay, so we know that Y is a right inverse of A. Okay, so I'm using the fact that Y is a right inverse of A. And here when I say right inverse, it's a special case of being an inverse. It just means that in this situation it just means the first equality. Okay, that A times Y is identity. Okay, so we know that in fact that Y is also a left inverse, but I'm just using the fact here that Y is a right inverse, and I'm trying to highlight very critically what assumptions we're using, which is always good in a math proof. So Y is a right inverse for A. Okay, so Y is a right inverse of A. And now we know that by associativity, okay, so everything is very precise here. By associativity, multiplying A and Y and multiplying X on the left is the same as X times A times Y. Okay? That's associativity. So I'm going to write this. That is associativity of the group operation. So everything is crucial. You know, this is where, associativity, once you prove something like this, that inverses are unique, and you do a lot of group theory, implicitly you're using associativity. So associativity comes up, we just take it for granted once we get used to it. But when we're proving things, it's important to be very precise. And here, X times A times Y, well, we know that X is a left inverse for A. Okay, we know E is equal to X times A, so this is E times Y, and that is because X is a left inverse for A. Okay, so this is X is a left inverse for A, which again is a special property of X being an inverse. X is both a left and a right inverse. I'm just highlighting, you could just say X is an inverse for A, but I'm highlighting that we're only using the fact that X is a left inverse for A, and then we use the fact that E is the identity to then conclude that this is equal to Y. So the first equality and the last equality are because E is an identity, and since X and Y were arbitrary, we have used the fact that X is a left inverse and Y is a right inverse to say X is equal to Y. Now as practice, math is always good to practice things. I encourage you just, after you watch this video, maybe tomorrow or a few hours from now, and come back and drop a comment, just try to explain how you do the same argument when X is a right inverse for A and Y is a left inverse for A. So only using that, try to do the same argument to say that X is equal to Y. Of course, it would be the thing. I'm not going to say anything more. I'll just let you do that just to practice and try to see how to come up with this, okay? Because I made it look easy, but it takes some thought to actually come up with. And we've highlighted all the group axioms, and it's very crucial here. You could have an element having multiple left inverses in a group, okay? Or in a, not in a group, but in a monoid, okay? So in a structure where you have an identity, you have associativity, you have closure with respect to the binary operation, you could have situations where you have an element, it has multiple left inverses. Okay, left inverses need not be unique. So we are knowing that, you know, inverses are unique. So we're basically saying that if something's a right inverse and something's a left inverse for the same element, they have to be equal. So in other words, in particular, inverses are unique, but left inverses need not be unique. If you can come up with an example of a monoid where that's true, that's my challenge to you. That's a tricky exercise, but I gave an example in another video where I showed that identities, left identities, need not be unique in a semi-group where you only have associativity. So thanks so much for watching. I hope you love this proof. And I'm a professional mathematician. I research group theory. So what better opportunity is there just to learn in short snippets the fundamentals of group theory? Check out my playlist here on group theory, which is growing steadily and has lots of different concepts. It's going to get very advanced, very basic, whatever you need, and also a video suggestion for you that you're going to love. I'm going to see you in my next video and wish you all the best.